Hello ladies and gentlemen, I'm back. We're going to move on with this filtering. I've skipped over several examples that are on the slides on my website in a PDF form with note pages so you can take notes, but also the PowerPoints themselves so you can go through them and step by step and see how the animations, see what the author intends to show you in the order they intend to show you. So now we're going to do the reverse. We're going to figure out the transfer function from the Bode plot. And we got this curve. We got this curve. We're going to look at region A first. Now, it's not 0 decibels, so you're going to have a constant. The fact that it's not 0 means you're going to have a constant. The fact that it's not rising at 20 decibels a decade, and that when you go down to 0 radians per second, you're going to get a negative infinity decibels. You're going to get zero gain. Zero gain means there's an omega or an omega squared, omega cubed, etc. times the numerator. That is not happening here. So the first zero or pole is going to be over here. So first the constant term. Next, 20 dB per decade drop. That means there's a pole. Because with a pole, as the frequency goes up, the gain goes down. So it's a simple pole, and it's at a angular frequency of 1/10, which can be written like this. Here's the 1/10 right there. J omega divided by a 10th plus 1. Okay, C, you're coming back to flat line. That means this is still going on. This still keeps dropping. That means we have something compensating that's rising, which would be a 0 in the numerator. Okay, and that's at the angular frequency of 1/2 of a radian per second. And you can write it like that, 1/2. D, now you're dropping again another pole at 3 radians per second. And then E, another pole at, it looks like 20 radians per second. Now you just construct a function. These are in the numerator. The zeros are in the numerator. There's the 0. The constant multiplier is in the numerator. Constant. The simple 0. Then all the poles, these 3 poles, are going to be in the denominator. Okay? That's it. It's not too tough, is it? You can, now remember, real curves have curvature. They do this kind of, they're smooth, and they kind of show things continuously. Take the asymptotes. When you're analyzing a plot, take the asymptotes. Take a ruler and a straight edge and figure out, well, asymptotically, what is it doing? And then this region will be, won't be accurate, but you'll be able to get the poles and zeros. And then you can put it in your computer model and get all the, duplicate the graph. Here, the slope is -40. What this is telling us, might be one of two things, and it's the first thing I'm going to talk about. Is the last two poles. They don't have the same root, so it's just the product of the two. If all of a sudden you had something, you were coming along, and all of a sudden you dropped at 40 decibels per decade, that would be a double pole. So you'd have a J omega over what frequency do we want? I put it at 3 radians per second. So 40 dBs per decade suddenly at one point. This is not sudden. It goes down to 20 and then it goes down to 40. But if it were sudden, you'd have this situation. Okay, your turn. We're going to talk about resonance now. And to do that, I want to jump back a bit. There we go. And so we have the formula of the equation. Okay. Where that is, we have resonance when we have the j omega squared. When we have this kind of thing going on, the transfer function has this square term. Resonance looks like this, depending upon your damping, which is zeta. There we go, zeta. Depending on your damping and how big the damping factor is, you know, small to big, kind of follows this curve, you will have resonance. Now let's go back to the slide we were on. So you see the shape of the curves, and where were we? Resonance, there we go. That's the slide we were on. So we can write impedance. I'm going to choose a different color for the pen. The author uses red so much, I want to be sure and have a color that contrasts. So we can write Z like so, and we have an imaginary part of Z and the real part of Z. Omega naught is going to be root 1 over LC when it makes this term equal 0. The imaginary part equals 0. Imaginary, yes, that's resonance. Right here is resonance. So we have the resonance frequency quality factor. For this circuit, the quality is given by this omega 0, L over R, or 1 over CR. We're going to see more about quality in a little bit, and we can write it like this without the omega factors. So the impedance reaches a minimum with this series circuit. If you plot impedance versus frequency, this is what you get. It starts out capacitive. Capacitive drives it. Capacitive is the largest impedance for low frequencies. Inductive is the largest impedance for high frequencies. Okay, I'm going to stop here We'll pick up the next slide next time.